take a closer look at the differences between these structure types to better understand why we use a geogrid reinforced wall, for example, in one application and a gravity wall or crib wall in another. As mentioned in SRW's 101, we discussed two basic structure types, the geogrid reinforced wall and the gravity wall, which can be constructed in a few different forms. In general, a geogrid reinforced wall is the most economical type of wall to construct, but also requires the most space, with a depth of reinforcement approximately 60 to 70% of the wall height or more. The gravity wall requires more concrete, whether in the form of large units or a crib, so it's typically more expensive, but may require less room to build it, usually around 30 to 50% of the wall height. Notice that I say may. A big part of what I want to address in this section of the training is some of the myths around large gravity walls, particularly in the context of competing against them. As a quick review, the geogrid reinforced wall is actually just another form of a gravity wall. We create a large composite gravity mass composed of a block facing, geogrid reinforcements, and reinforced fill material. In most applications, there are two main factors that dictate the geogrid length in a wall. The first is the design methodology being used. On most private projects, the NCMA design methodology is followed, which requires a minimum of 60% base to height ratio or 4 feet of geogrid. So even if the wall is 3 feet in height, it cannot work as a gravity wall, The minimum geogrid length would be 4 feet. For public projects such as transportation or other infrastructure, the AASHTO, or American Association of State Highway Transportation Officials, design methodology will likely govern. Currently, AASHTO requires a minimum of 70% base to height ratio or an 8-foot geogrid. Again, even if the wall is relatively low, a minimum of 8 feet of geogrid is required. The second main factor is known as the anchorage length of the geogrid. We're not going to go into major detail on this, but with a simple example, we can easily understand the mechanism behind geogrid anchorage. Taking a quick look at this diagram, we can see that the hatched portion behind the SRW blocks is a wedge shape. This is known as the active zone or the failing zone of the reinforced mass. The red line that runs at an angle behind the active zone is known as the failure plane. This defines the active wedge. Beyond the failure plane, we consider this portion of the reinforced mass as passive or stable. The basic concept behind reinforcing soils is to then use the geogrid reinforcement layers as tiebacks to anchor the geogrids into the passive or stable zone so that the active wedge is restrained from sliding down the failure plane. A simple demonstration of this concept of active and passive zones and the failure plane between the two of them is the sandcastle example. If you were making a sandcastle with a bucket and you pack the sand into it tightly, as long as there's a little bit of water in the mix, you can remove the bucket and it will stand basically vertically. However, over time, as the sand dries out and the water is not there to hold it all together, which is a force called cohesion, the sandcastle then relies only on the friction between the sand particles to stay standing. These friction forces between the sand particles are limited, and a wedge of the sandcastle will naturally break away as we are showing here. The plane that the wedge breaks away on is known as the failure plane. The angle of that failure plane is directly related to how high the friction forces are between the sand particles. The higher the friction forces, the steeper the angle of the failure plane will be. Different types of soils, based on the size and shape of the particles, have different capacities to generate friction between the particles, a measure known as the internal angle of friction of the soil. This is a key parameter in all SRW design. Soils such as gravels and sands have higher values for their internal angle of friction, ranging between 32 degrees up to 45 degrees and higher. Fine-grained soils have lower friction angles. Going back to our reinforced wall diagram, we can relate the soil here in the reinforced zone to the sandcastle. We are designing the wall to restrain the active wedge that wants to fall away. Because the failure plane propagates up at an angle from the bottom of wall, usually around 60 degrees when using a good quality soil, We can see that as you get closer to the top of the wall, there is less anchorage length, or less geogrid is within the passive zone. This explains why geogrids are often longer near the top of the wall than at the bottom. This diagram also explains why using good quality soil, which will give us a steeper failure plane, will result in shorter geogrid lengths at the top. And by comparison, when using poorer quality reinforced soil, which gives us a shallower plane, the geogrid lengths often need to be longer at the top of the wall. The NCMA requires that a minimum anchorage length of 1 foot is required beyond the failure plane. Understanding this concept provides some insight into how competitive designs can differ substantially. If one designer assumes very high friction angles for the reinforced zone and another designer assumes more average friction angles for the reinforced soil, the geogrid length can be substantially different. The assumption may be buried in the fine print, and only once the contract is awarded to the lowest bidder is that important detail brought to light, and in many cases the geogrid length ends up being closer to what was assumed by the more conservative designer. Either way, the design methodology and anchorage length typically have the most impact on geogrid length. We now understand how the basic dimensions of the geogrid reinforced wall are determined, so the next step is to understand why a geogrid reinforced wall is typically the most economical type of structure to build. First, most of the mass is composed of backfill material, not concrete blocks, which is less expensive, even when it is imported reinforced soil. Second, geogrid is relatively inexpensive and performs well to create the gravity mass. In a fill situation where we are adding height to the site or filling the site, we are backfilling to raise the grade anyway, so this is where geogrid reinforced walls are really a natural fit. Looking now at gravity walls, let's see why the depth of the wall is usually less than a geogrid reinforced wall. There are two main reasons for this. First, there is no specific minimum limit enforced by the design methodology, like the 60% base to height ratio imposed by the NCMA. Second, we are not anchoring back into the passive zone of the backfill like in a reinforced wall. The gravity wall is basically self-contained. As we have noted, the base to height ratio of a gravity wall is between 30 to 50%. However, while the possible range is less than that of a geogrid wall, in most cases, when you account for everything, the difference is not as much as you would think. Gravity walls are best used when site space constraints exist, such as property lines or existing structures, and cut situations where excavation should be limited and or it's difficult disposing of the material. The three classic or traditional gravity options are the single depth gravity wall, which is usually for walls up to about 5 or 6 feet in height. Then the multi-depth gravity wall, which is practical for walls up to about 9 feet in height. And finally, the crib wall, which allows you to construct greater heights, such as 25 feet or more. More recently, Risi Stone has included 3 additional gravity structures as potential design options. The first is a type of gravity wall that is created with a block facing, then backfilled with a permeable concrete mixture known as no-fines concrete. I explain this more in the next few slides, but basically we create a composite gravity mass by turning the drainage layer that is typically present behind a gravity wall into part of the gravity structure. The second type of new gravity wall is the incremental multi-depth wall. This is basically the same as our traditional multi-depth wall, but instead of having very large base units, we create the wall depth or mass by incrementally adding more units back to back as shown. We require layers of geogrid between these units to keep the mass intact, but this allows us to basically create any depth of wall with just one module. Finally, the third new option is a hybrid geogrid gravity wall. To create the mass here, we have a front wall and then a back wall similar to a crib that is filled with gravel through the middle and joined together with layers of geogrid. This back wall essentially acts as the passive zone in a normal grid wall and anchors the geogrid end facing back. Depending on the situation and conditions, this option may be the most economical of the three. As mentioned, we will take a closer look at no-fines concrete, the first of the newer gravity options discussed. No-fines concrete is basically exactly what the name indicates, a concrete mix with little or no fine content, primarily made up of one size of larger aggregate, water, and cement. It was originally developed in Australia over 30 years ago. Because there are no fines in the concrete, it has large voids present between the aggregate, which allows water to flow through, making it permeable. The mix is poured behind the SRW unit, so there is no need for compaction or very little. As the no-fines concrete cures, it stabilizes into a solid mass and adheres to the back of the SRW units, basically turning this drainage layer into part of the wall. As you can see from the photo, I am not totally sold on the idea that long term this mix will fully adhere to the back of every type of block. So Risi Stone has introduced small layers of Geogrid as an extra assurance to combine the facing with the no-fines backfill. The unit weight of no-fines concrete is substantially lighter than regular concrete due to the lack of fines and the presence of voids, estimated to be around 100 to 135 pounds per cubic foot. The aggregate size is between 3/8 of an inch and 3/4 of an inch, with a water-cement ratio of 6:1 by weight. Because it is still a wet concrete mix, the maximum lift thickness should be limited to 16 inches, and it is recommended that the system be left to cure after each 4-foot segment of wall is constructed. There are a couple of main advantages to no-fines concrete. First, the fact that it eliminates the need for the additional 1 foot of drainage behind the wall, as we see with traditional gravity walls, means the overall depth of excavation required is 1 foot less. This might not seem like a lot, but in situations where property lines and tight spaces are present, this can be the difference between fitting into a site and not. Second, because the no-fines mix does not require compaction, the installation can be significantly faster than other options. There are also some disadvantages with no-fines concrete, the main one being price. No-fines concrete will be 2 to 3 times the price of regular aggregates, but I've found that this varies considerably from region to region. But if you consider reducing the amount of excavation required and the effort and labor to compact and fill regular aggregates, it may work out to be still more economical. From a wall supplier point of view, no-fines concrete does not provide any additional benefit, as most of the wall mass is created by a product that you are not supplying. But this is really no different than a Geogrid reinforced wall. Finally, as mentioned, I do have some concern about the long-term adherence of the back of the block to the backfill material, the no-fines concrete, which we deal with by adding small layers of reinforcement as shown. The second type of newer multi-depth gravity wall we have discussed is the incremental multi-depth. This is where we place multiple units back to back to create a larger gravity mass. This is typically only done with machine-placed walls, and experience has shown that it is really only practical to do up to about 2 or 3 blocks deep. As a side note, the newer smooth-faced machine-placed walls are ideal for this type of solution, as the units can be placed face-to-face easily. The advantages of this approach are, we are creating mass with a single wall module, which makes ordering and stocking the units on site much simpler than having multiple units with varying depths. And 2, the majority of the wall mass is being composed of a product that you are supplying. The disadvantages of this approach are the fact that it would be more expensive than a typical Geogrid reinforced wall, and it would be time consuming to lay multiple units back to back, particularly on the base course. Again, practically speaking, this type of structure would probably only work for walls that require 2 or 3 blocks in depth. When we need to create greater wall depth in our gravity structures that exceed what we can practically do with multi-depth or incremental multi-depth walls, Another option is the hybrid grid gravity wall. Basically, we are creating a type of geogrid crib where the facing is connected to a back wall with a geogrid instead of concrete tiebacks. As with a crib, the space between is filled with compacted free-draining gravel. This type of hybrid structure has some of the benefits of a grid wall, as we are creating some of the mass with fill, but avoids some of the geogrid design limitations we discussed earlier. Practically speaking, we would require at least 18 to 24 inches between the front and back wall to allow filling and compaction equipment. So from a wall depth point of view, if our SRW unit is 1 foot deep, for example, the minimum overall gravity wall depth would be around 4 feet deep. This results in a starting wall height of around 8 feet, assuming a 50% base to height ratio. So we can see that this type of gravity structure is definitely for higher walls, but may be a good option for a portion of a particular wall. The advantages of the hybrid gravity wall include higher gravity walls at a lower cost. More of the mass is created with SRW units, and it's very easy to create a custom wall depth. Unlike a traditional crib system where the tiebacks are made of concrete and they are a set depth, we can easily modify the geogrid length to create the optimal depth we need. The disadvantages include the additional back wall is more costly compared to a geogrid wall, a typical geogrid wall, and it could be more time consuming to set the front block and the back block compared to just one large block, such as the massive wet cast systems that are available on the market. To illustrate how this concept was used on a real project, we recently incorporated a hybrid gravity wall into a section of a large geogrid reinforced wall in Aurora, Ontario. As shown in this diagram, a portion of our wall came within a distance of 0.5 of the wall height to a proposed residential structure. We wanted to ensure that these structures remained independent of each other, and as we have learned, a typical geogrid reinforced wall would have reinforcements extending back 60 to 70% of the wall height, which in this case would be under the house. The design concept was to construct the hybrid wall, and as it is being constructed, backfill behind the wall with a low-strength concrete as shown. By doing this, the footing loads from the house are transferred below our wall, and these structures remain independent. This arrangement was only done for a small section of the wall, but it allowed us to provide a complete solution for the project, using the more economical geogrid reinforced walls wherever possible. The two most important factors when determining how high you can go with a gravity wall are 1, the quality of the retained soil, and 2, the slope or loading above the wall. I want to stop here and really highlight the next point. We have discussed how in tight spaces a gravity wall may provide a solution. However, this really depends on the quality of the soil being retained. In many cases, if we have an average native soil such as a clay or silty clay that we are retaining, the difference between the depth required for a geogrid wall is almost the same as the depth required for a gravity wall. The frustrating part from a design point of view is that the quality of the retained soil, or the internal angle of friction that we discussed earlier, is often estimated because of a lack of proper information. In this example, we have a 10-foot high wall with a 3-to-1 slope above it, and we are retaining a native clay material. We can see that the grid wall requires 6.5 feet of geogrid, and the gravity wall requires a total of 6 feet of depth, including 1 foot of drainage layer. So in this case, they are really almost identical in terms of depth. If we increase the quality of the retained material to something slightly better, we can decrease the overall depth to 6 feet for the grid wall and 5 feet for the gravity wall, which is still not significantly different. Only when we get to very high quality retained soil, such as pure sand and gravel, do we start to see a significant difference. In this example again, we have 6 feet of Geogrid versus 4 feet of gravity depth. But how often do we see this situation? So we can then draw the conclusion that the gravity walls only save significant space when the retained soil is of very high quality. So when competing with large wet cast gravity walls on the market, we really have to question what assumptions are being made on the retained soil. If a preliminary design is used for a bid and it is conveniently assuming very high quality soil, but it is full of disclaimers, we need to question that. The other big elephant in the room when we talk about the space availability is the fact that if it is a cut situation and we are near a property line, we still must be able to excavate over the property line to build the wall safely. Typical occupational health and safety guidelines indicate that excavations must be conducted at about a 45-degree angle. This means we are cutting back nearly as far as the wall is high. So in summary, the only time the gravity wall would be of benefit in this case is if there's a property line less than 6 feet away, so the grid wall would not fit in, and there is permission to excavate into the neighboring property temporarily and replace the existing soil with a high quality sand and gravel. So the bottom line is many competitors talk about being able to build much higher walls in less space than a grid wall, but the reality is much more complex, and there are really only very specific situations where this is the case. Looking at the same 10-foot wall, if we have a cut situation, but with no property line issue, is there any advantage of going to a gravity wall with respect to excavation and backfilling? Well, not really. With a grid wall, we have 6 feet of depth. However, we can backfill with native soil beyond the grid zone. With a gravity wall, to reduce the depth, we would need to backfill the retained soil with a high quality sand gravel. So the excavation and backfill is about the same. In a fill situation, is there any advantage to a gravity wall with respect to excavation and backfilling? As we discussed, if the retained soil is the same for both, the overall depth of wall will be similar, and generally a grid wall should be more economical than a gravity wall. There is a reason Geogrid was invented. So to summarize, there are many options available for structure types, and we can mix them within the same wall. The bottom line is that a gravity wall usually only makes sense when space is limited and only in specific soil conditions. The best option is still the Geogrid reinforced wall with a machine placed block, in my opinion. The second best option from a cost point of view would be a hand placed Geogrid reinforced wall. Finally, the hybrid gravity or multi-depth gravity could be a good solution depending on the height required and the space limitations.